సబ్మిట్ చేసుకోండి సార్.
స్టార్ట్ చేద్దామా?
టూ 90 ఉన్నాడు సార్, స్టార్ట్ చేయండి.
$400 స్ట్రెంత్.
అవును సార్, 420.
ఆసిఫ్ సార్,
సార్
స్టార్ట్ చేయండి. వీళ్ళు వచ్చేసరికి చాలా లేట్ అవుతుంది సార్. మెల్లగా ఒక్కొక్కడు జాయిన్ అవుతా ఉంటారు.
మీటింగ్ లాక్ చేయాలి. ఇంకా అలా అయితే ఒక రోజు మీటింగ్ మొత్తం లాక్ చేసేస్తే తెలుస్తుంది.
రివిజన్ లో చేద్దాం. టైంకి రాకపోతే రివిజన్ షెడ్యూల్ లో లాక్ చేయటమే. రివిజన్ షెడ్యూల్ లో సార్ లాక్ చేయటమే టైంకి రాకపోతే.
చలో, come to next topic beta, X-rays. The first one is your X-ray protection. Okay, see, the X-ray protection is an example for the quantum nature of electromagnetic radiation beta. The protection of X-rays is example of quantum nature of electromagnetic radiations. The protection of an X-ray is an example for what beta? Quantum nature of your electromagnetic radiations. And X-rays are produced when rapidly moving electrons that have been accelerated through a high potential difference. accelerated through a high potential difference when they strike a metal, target. Okay, so X-rays have been produced when rapidly moving electrons. How? When rapidly moving electrons ni manamu okavela accelerate cheyagalugute by applying very high potential difference. So if they are made to strike a target element, from that target element some rays have been producing. That rays are called as of your X-rays part of relation. Okay, they have been discovered by a scientist called as of your Rontgen. This was being discovered by your Rontgen, a scientist called as of your Rontgen part. When highly energetic electron strikes any metal target beta, electromagnetic radiations are coming out. So the wavelength of this X-rays is in the order of 1 angstroms initially. Nature of X-rays was not known. Later on, these X-rays were being identified as a few very highly energetic photons. So it was being produced very accidentally beta. When Rontgen was doing some experiment in his lab particulation, by mistake, when in highly moving electrons are being targeting or being strike the metal target, some radiations were being coming out, which was being seen in his graph. So he couldn't able to understand at that time what are these part of your rays which have been coming. So as he was not knowing, so he has given the name for that one as of your some X-rays. Till from that point to till now, we are just defining that rays as of your X-rays particulation. So X-rays are being what example of your quantum nature of electromagnetic radiations, and they are produced when a rapidly moving electrons have been accelerated through a high potential difference, and when they strike a metal target particulation. Okay, and X-rays were being discovered by whom? X-rays were being discovered by your Rontgen, isn't it? So what is the condition? When highly energetic electrons strike a metal target, electromagnetic radiations comes out. Okay, the wavelength of X-rays is order of 1 angstroms. Okay, so what are these X-rays? I can say that X-rays are highly energetic photons, which have been coming out of your target elements. I'll tell you how they have been coming out. So just now, remember what an X-rays. When highly energetic electrons strikes a metal target, electromagnetic radiations have been coming out. These electromagnetic radiations which are coming out are having a wavelength of order of how much for me? 1 angstroms. And these X-rays are what? Highly energetic photons. X-rays are your what? X-rays are your highly energetic photons, and the range of the wavelength is almost all the wavelength of X-rays is of your 1 angstroms particulation. So what is this one? When a highly energetic electrons strike a metal target like nickel particulation, the rays which have been coming out are electromagnetic radiations, which are having the wavelength in the range of 1 angstrom, and these are called as of your highly energetic photons. They are called as of your highly energetic photons particulation. Originally, X-rays were being produced in a tube called as of your Coolidge tube beta. So I can write here right now. X-rays were produced initially in Coolidge tube. And a tube which is right now a vacuum condition like this. And just draw roughly the diagram. Chudo. This was some vacuum tube like this. Okay. In this one there was a filament, like మనకు బల్బ్ లో ఫిలమెంట్స్ ఉంటాయి చూడండి, అలాంటి ఫిలమెంట్. Okay, and on this filament there is a cover like this. Okay, and this one was being connected to your very high potentials. This one was being connected to your potentials of negative, positive, negative, positive, negative, positive, like that very high potentials they have been connected to your V. And here somewhere we are having a target element. ఇట్లా మన దగ్గర ఒక టార్గెట్ ఎలిమెంట్ ఉండే. Okay, so this one was of your target element, and here this was the area on which the rays have been incident, and this was being connected by your coolant, water flow అవ్వడానికి. ఇక్కడ నుంచి కొంచెం వాటర్ ఫ్లో చేయించే వాళ్ళం ఇట్లా, so that water was being incident in this one like this, so water was being coming out from this one. What is the role of this water అంటే, ఈ highly energetic electron దీని పైన పడినప్పుడు ఇది హీట్ ఎక్కేది, దీన్ని చల్లబడడానికి విల్ బి యూజింగ్ ద వాటర్ ఫ్రమ్ దట్ వన్, దట్ ఈస్ కాల్డ్ యాజ్ ఆఫ్ యువర్ కూలెంట్ పార్ట్ ఆఫ్ రిలేషన్. అండ్ ఈ పార్ట్ ని ఏమైతే తీసుకుంటున్నాం మనము, దిస్ పార్ట్ ఈజ్ యువర్ టార్గెట్. దిస్ పార్ట్ ఈజ్ నథింగ్ బట్ ఆఫ్ యువర్ వాట్ టార్గెట్. Okay, and this was the basic setup right now. This one is your filament, this one is your filament, and from here we are seeing some radiations, it is some potential, and this one was being connected to this point, this one, and this one was acting as of your anode, positive terminal, and this one was negative terminal, and this one is your glass chamber, and this was been producing the electrons in this one. So ikkada nunchi some electrons were being produced. Okay, and they started moving with very huge velocities like this. Okay, and the moment they were been hitting this target element, from this one certain radiations were being coming out. At that time they were not known, so certain radiations were started coming out from this one. This radiation we call it as of your X-rays. Okay, so this one was a cathode, and this one is your cathode, and this one is your anode, and this is your water. Okay, so originally the X-ray was being produced in the colloid tube. A colloid tube is nothing but the electrons are emitted by the filament. This is the filament which has been connected to some low potentials, like say from positive terminal, and this is your some negative terminal, some 5 to 10 volts మాత్రమే. ఇది some 10,000 volts వరకు ఉంటుంది ఈ పొటెన్షియల్, వెరీ హై పొటెన్షియల్ ఇది. సో ఈ పొటెన్షియల్ వల్ల ఏమైపోతుందంటే 5 to 10 volts వల్ల ఈ ఫిలమెంట్ గెట్స్ రెడ్ హాట్, అండ్ ఫ్రమ్ దిస్ వన్ ఎలక్ట్రాన్స్ ఆర్ బీన్ మూవింగ్ అవుట్. దిస్ ఎలక్ట్రాన్స్ ఆర్ బీన్ మూవింగ్ అవుట్. దీనికి ఒక ఫిలమెంట్ అని, ఈ ఫిలమెంట్ పార్ట్ ని మనం ఒక మెటల్ ప్లేట్ తో కండక్ట్ చేసి ఒక హై పొటెన్షియల్ కి అప్లై చేస్తున్నాం. ఈ హై పొటెన్షియల్ వల్ల ఏమైపోతుందంటే ఈ ఎలక్ట్రాన్స్ ని మనం యాక్సిలరేట్ చేయగలుగుతున్నాం. We can increase the acceleration of this one basically, isn't it? So the electrons emitted, I can write that point here right now. The electrons emitted by filament, by your filament, are accelerated by potential difference to hit the target with a very high speed, మీరు ఐరన్ మ్యాన్ చూసింటే, in the first part when he gets escaped from the cage, he comes to the home and start working on his suit basically. So he will be making the metal by which he will be incidenting n number of your rays, so that a metal can be produced by the different bombarding. Okay, ఈ ఎలక్ట్రాన్స్ ఎమిట్ అయ్యేదానికి యాక్సిలరేట్ చేయడానికి మనం ఇది యూస్ చేస్తాం. ఇక్కడ నుంచి వెరీ స్మాల్ పొటెన్షియల్ కాబట్టి ఎలక్ట్రాన్స్ ఓన్లీ మెల్లమెల్లగా ప్రొడ్యూస్ అవుతాయి. ఆ మెల్లగా వచ్చిన ఎలక్ట్రాన్స్ ని వెరీ హ్యూజ్ స్పీడ్ ఇవ్వడానికి దాన్ని మనం ఒక హై పొటెన్షియల్ ని అప్లై చేస్తాం. హై పొటెన్షియల్ అప్లై చేయగానే ఏమైపోతుంది, దిస్ ఎలక్ట్రాన్ విల్ గెట్ ఎ స్పీడ్, వెరీ హ్యూజ్ స్పీడ్. విత్ దిస్ స్పీడ్ ఇట్ విల్ హిట్ ది టార్గెట్, అండ్ ఆ టార్గెట్ నుంచి ఆ ఎలక్ట్రాన్ లోపల పోగానే ఏమైపోతుంది, బికాస్ ఆఫ్ ది ట్రాన్సిషన్ certain radiations have been coming out in the form of what, electromagnetic radiations. That electromagnetic radiations at the time have been called as of X-rays, which are your highly energetic particles. Okay, so now what we are writing right now, the electrons emitted by the filaments are accelerated by the potential difference to hit the target with a very high speed. So these electrons, whatever is being produced, these electrons are stopped, these electrons are stopped by the target, or been stopped by the target, and in the process X-rays are emitted. X-rays are emitted. Clear? X-rays is actually inverse process of photoelectric effect, beta. X-rays emission is inverse of photoelectric effect. Okay, so in photoelectric effect ఏమవుతుందన్న, in photoelectric effect energy of your photon is converted into kinetic energy. అంతే కదా, converted into kinetic energy. Metal surface పైన మనము rays of photons ని వేసినప్పుడు that have been coming out, that electrons are coming out with your certain kinetic energy particulations. So in photoelectric effect, energy of the photon is being converted into the kinetic energy of your electrons. Kinetic energy of your electron. In X-rays production, kinetic energy of your electron is converted into energy of photon. It's converted into energy of your photon. Okay, so work function of metal is neglected. Work function of metal is neglected here. Phi of your metal is neglected. అంతే కదా, ఎందుకని వెరీ హైలీ ఎనర్జెటిక్ ఫోటాన్స్ వెన్ దే ఆర్ బీన్, ఈ ఎలక్ట్రాన్స్ దీనిపైన పడినప్పుడు రేడియేషన్స్ వస్తున్నాయి ఇన్ ద ఫార్మ్ ఆఫ్ యువర్ ఎనర్జీ. దట్ రేడియేషన్స్ యూ ఆర్ కాలింగ్ ఇట్ యాజ్ ఆఫ్ వాట్, ఎక్స్రేస్. అంటే వీఆర్ కన్వర్టింగ్ ది కైనెటిక్ ఎనర్జీ ఆఫ్ ది ఎలక్ట్రాన్ ఇన్ టు ది ఎనర్జీ ఆఫ్ యువర్ ఫోటాన్స్. ఇన్ photoelectric effect, energy is being converted into your kinetic energy part of a relation, isn't it? So that is a basic difference between them. So we can say that photoelectric effect is inverse of your X-rays part of relation, or X-rays emission is your inverse of your photoelectric effect part of relation. ఒకసారి చూడండి. So what is happening in X-rays right now? When electrons of your really highly energetic particles are being incident on this target element, certain radiations are being coming out. That radiations we are calling it as of your X-rays particulation. X-rays emission is your inverse of your photoelectric effect. It is your inverse of your photoelectric effect. X-rays is your inverse of your photoelectric effect. In photoelectric effect, energy of photon is converted into kinetic energy of your electron. Whereas in the X-rays, in your X-rays production, kinetic energy of the electron is being converted into your energy of your photon, and work function of the metal is neglected. Work function of your metal is neglected for the given condition. Clear? Sure. Come to the next slide heading. Continuous and characteristic X-rays. Characteristic X-rays. Continuous and characteristics of your X-rays. Okay. Now see, when this experiment was being doing on, the scientists started making a graph for that one. So they analyzed that this wavelength of the X-rays which have been coming out from this collegiate tube was being plotted against the intensity of your wavelength, isn't it? So as the intensity was increasing, the wavelength was being increasing after certain minimum particulation. So they grabbed a graph something like this. If we analyze wavelength in X-rays, wavelength in your X-rays, which is coming from collegiate tube, which is coming from your collegiate tube, and plot a graph with variation of intensity with wavelength. Intensity with your wavelength. See how we got right now. So you have got a graph something like this. So this one was your intensity, and here is your wavelength. When intensity was being increased initially, nothing was being found. Still you increased in intensity, still the wavelength was being strong. At a certain point somewhere here, a minimum wavelength started increasing like this. So from this one, the wavelength started as the intensity was being increasing like this. Then suddenly there was a sharp rise, then again your fall. Then again there was of your sudden increase. Again there was of your decreased particulation. And like this, the radiations have been going on like this. So they call this one as of your K alpha and this one as of your K beta particulation. Okay. That means what I mean to say is there is minimum wavelength below which the X-rays we are not emitted particulation, even though we have been intensity has been increased. So there is minimum, there is your minimum wavelength lambda minima below which no X-rays is emitted. Okay, this is the minimum wavelength. So this lambda minima is known as cutoff wavelength or threshold wavelength. Lambda minima is known as of your cutoff wavelength. This is known as cutoff wavelength, or this is called as of your threshold wavelength. Threshold wavelength. Okay, so this is the minimum wavelength. This is the minimum wavelength below which the X-rays have been not produced particulation. For certain wavelength, intensity is very large beta, which has been marked as of a K alpha, isn't it? K beta. These are called as of a characteristics X-rays. Other wavelengths, the intensity variations gradually and they are continuous. Continuous. కొన్ని metals కి మాత్రం for certain wavelengths there was sudden increase. They are called as of what? Characteristics part of relation. The remaining was of what? Your continuous part of relations. Other wavelength intensity varies gradually. These are called as of your continuous X-rays. And there are origin of your two types of X-rays have been possible better. One is your continuous X-rays. Another one is about your characteristics types of your X-rays part of your relation, isn't it? So I can write here right now for certain wavelength, for certain wavelength, for a certain wavelength, intensity is very large. Intensity is very large. Very large. They have been marked as K alpha, K beta. We'll do it this one in detail in the coming part. So these are called as of what? These are characteristics of your X-rays. These are your characteristics of your X-rays. For a particular wavelength, they are giving the radiations. So other wavelengths of intensity varies is gradually. They are called as of your continuous. That means the electrons which have been accelerated by potential difference has kinetic energy. When it hits the target, the electrons enter the target. It loses the kinetic energy, comes to the rest inside the metal. And before stopping, the electrons make the several collision with the atom of the target. And each collision, this will be produced. And it is central part of your nucleus, isn't it? One electron has been revolving in this one, beta. Another electron has been revolving in this one. This is the target element anukundam. And another one has been in this one right now. Okay, so you know that this one is K shell, L, M, go on like this one. So we are having one electron in this one right now, 2. And next one is nothing but of your 1, 2, 3, 4, 5, 6, 7, 8, like that, isn't it? So when these energetic photons, were being incident, when electrons, this one has been coming with very huge speed, they enter into the target element like this, and they lose the energy. They lose the energy, and during that, before they enter into this one, certain rays will directly pass very near to this one like this, and certain part will be fall right now like this. This rays, when they are losing the kinetic energy, the rays which have been coming out called as of your X-rays, and certain part will be hitting, like say if I need to remove this electron particularly, so this electron, when it is been heated particularly, this electron is being coming out exactly, and this vacancy is being filled by the electron which is being present in the outermost. So ikkada nunchi ikkada vache energy manam emantunnam manamu characteristics type of your X-rays part of your relation. Okay na? Is that clear? Is that clear? అంటే ఒకవేళ ఎలక్ట్రాన్ కంటిన్యూస్ గా ప్రతి ఆర్బిట్ లా స్ట్రైక్ అవ్వకుండా పోతే ఏమైపోతుంది? కంటిన్యూస్ ఎక్స్రేస్ హావ్ బీన్ ప్రొడ్యూస్. ఇఫ్ ది ఎలక్ట్రాన్ is hitting one particular electron, isn't it? If you are removing one particular electron from an orbit, then that is called as of your characteristics type of your X-rays. This is called as of your characteristics type of an X-rays, and this is called as of your continuous X-rays. అవునా కదా? లైక్ సే మనము ఎక్స్రేస్ డాక్టర్స్ యూజ్ చేస్తుంటారు ఫర్ ట్యూమర్, లేకపోతే ఏదైనా ఒక పార్ట్ ని తీయడానికో, లేకపోతే కరిగించడానికో, లైక్ లేజర్ ట్రీట్మెంట్ అంటాం. Like say kidney stones ni తీయడానికి they will be using the radiations. That means when the rays of a particular radiations have been incident on that kidney part, they'll be hitting only the target of your the kidney in where the stones have been present, so that they can melt the stone present in that one with their intensity part of relation. So if they are hitting a particular target, they are called as of your characteristics. If it is hitting complete body radiation, that is called as of your continuous X-rays part of relation. Okay now, so what is happening is right now, the electrons which have been accelerated by the potential difference has kinetic energy. When it hits the target, an electron enters the target. It loses the kinetic energy slowly and comes to rest inside the metal. So before stopping, the electron makes the several collisions with the atom of the target, and in each collision will be getting either continuous X-rays or your characteristics type of your X-rays. This point clear andarki? When this electron are being hitted to this target element, it will be hitting each and every orbit, so that at each and every orbit it will losing the energy, and the rays are been coming out continuously part. So they are called as of what? Continuous X-rays. But if you are hitting any particular electron, and if that electron is been removed, that is called as of your characteristics type of your X-rays. Clear for everyone? Is that clear? Chalo. So let us try to talk about the first one. What do you mean by your continuous X-rays? continuous X-rays. Continuous X-rays. So what is happening here is the kinetic energy of electron. The kinetic energy of the electron. The kinetic energy of the electron is reduced. Kinetic energy of the electron is reduced. A part of kinetic energy. A part of kinetic energy is converted into photon, is converted into photon, and another part into heat. Target పైన పెట్టడం వల్ల ఏమైపోతుంది, హీట్ ఎక్కిపోతుంది కదా, so that will be getting as heat. So the electron makes another collision with the reduced energy and so on. So the wavelength of X-rays and the energy of the photons are related by this given condition. So wavelength lambda is equals to your hc by your E part-F relation. So E can be 0 to your electron volt part-F relation. It can be from 0 to any electron volt. Hence the wavelength of this lambda will lie between hc by your electron volt to your infinity. Okay, so what do you mean by cutoff wavelength, beta? So the minimum wavelength at which the electro X-rays are being produced is called as of your cutoff wavelength. So that cutoff wavelength is being given by the relation minimum wavelength and the lambda minima will be equal to your hc by your electron volt. That is nothing but of your energy. And here capital V is nothing but what? Potential. Capital V is your accelerating potential. Accelerating potential part-F relation. So lambda depends on V but not on the target. So lambda minima is equals to your hc by your V. So I can say that minimum wavelength lambda minima depends only on potential, only on capital V, but not on target, material, but not on your target material. So this is the minimum wavelength at which the X-rays are being produced. That minimum wavelength can be calculated by the formula lambda minima is equals to your hc by your E, where V is nothing but of your potential part-F relation. So the process of this, the above process of continuous X-rays is known as of your Bremingstrom breaking radiation process part-F relation. So I can write even this one as continuous X-rays. Continuous X-rays is known as Bremsstrahlung, or we can call it as of your breaking radiations. Breaking radiations or process part-F relation. Okay, so in the continuous X-rays, the minimum wavelength of the X-rays which has been required for the production of an X-rays is lambda minima is equals to hc by E into V. దీనికంటే తక్కువ ఉంటే మనకు X-rays అనేది continuous గా రావు. They are called as of your continuous X-rays part-F relation. Now let us try to talk about your characteristics type of your X-rays. Next one is about your characteristic X-rays. అంటే రిమూవింగ్ వన్ పర్టికులర్ ఎలక్ట్రాన్ ఫ్రమ్ ఏ పర్టికులర్ ఆర్బిట్. ఎల్ షెల్ నుంచి ఎల్ అవుతుంది, కే నుంచి అయితే కే అవుతుంది, ఆ కండిషన్స్ రైట్ నౌ. ఓకే, సో కంటిన్యూస్ X-rays are due to knocking off the electron on the inner electron beta. When accelerated electron collides with the atom of a target. Suppose an electron is knocked out from the K shell. A vacancy which is being created in the K shell is being filled by vacancy from what? Higher orbit. అవునా కదా? So I can write here right now. Continuous X-rays are due to knocking out of an inner electron when accelerated electron accelerated electron collides with atom of target material. Atom of your target material. Okay. Now see here. Suppose an electron is knocked out from K shell అనుకుందాం. From your K shell. A vacancy is created in the K shell. In your K shell. అది ఎవరు నింపాలా? ఇప్పుడు చూడండి దీంట్లో if the electron is being removed from your L shell, energy from the electron from your capital M will come to the L shell. If you are removing the electron from the K shell, energy from your higher orbit and L will try to take place of that vacancy and try to become the stable. That was happening in the given conditions right now. So suppose an electron is knocked out from the K shell, a vacancy is created in your K shell. Now to fill this vacancy, electrons jump from other orbits, from your other orbits. When such transition occurs, energy is being converted into a photon of your wavelength part of relation. So when the electron is being jumping, when such transition occurs, and energy hc by your delta E is converted into a photon, of wavelength, lambda is equals to hc by your delta E. X-rays emitted due to vacancy of K shells are called as what? K X-rays. Okay. X-rays emitted due to vacancy in K shell, your K shell are called K X-rays, are called as of your K X-rays part of relation. Okay. See, if this is your nucleus and if electrons are being present in the outermost orbit like this, ఇది టార్గెట్ అనుకుందాం. ఓకే, దీంట్లో మనకు ఎలక్ట్రాన్స్ ఉంటాయి, ఇక్కడ ఒకటి, here also 1 2, this one is 3, this one is your 4 5 6 7 and 8. Okay, so when electron is being vacancy, when I say for example when an incident electron is been hitting this particular atom, like say for example if I am hitting this ray of a light, this one is visual with a K shell, this is your L and this is your M. So when this particular radiation is being incident on this one, this electron is been knocked out, here vacancy is been created. Here right now vacancy is created. That vacancy is created is being filled by your this electron. ఇక్కడ నుంచి ఇక్కడ వరకు ఇది వస్తుందా right now? So this electron will take this position. So during that process, whatever the energy has been coming out, that is called as of your K alpha X-ray, K alpha X-ray part of relation. Clear? So this one is K nunchi K la vacancy create aithe electron which is coming from your L to your K is called as of your K alpha X-rays part of relation, K alpha X-rays part of relation. Clear? Clear? This is your incident electron beta. This one is your incident electron. When this incident electron is been incident on your K shell, vacancy which has been created in K shell is been taken from your L. So when there is a transition from higher to lower orbit, the energy whichever is been coming out is called as of your what? K alpha X-rays part of relations. I can write here one point here. If vacancy is filled by L shell, is filled by your L shell electron, then K alpha X-ray is emitted. In the same way, if vacancy is filled by M shell, by your M shell electron, comma, K beta X-ray is emitted. Okay. If vacancy is being created, in L shell, in your L shell, and filled by M shell, and filled by your M shell electron, then L alpha X-ray is emitted, and so on. Okay, so that is very important point. If it is from your L shell electron, that is known as K alpha X-rays. Then from your K beta X-rays from your L shell. If vacancy is created in L shell, then M shell has been created. That is called as of your L alpha X-rays part of relations. Very, very important beta. Try to remember these given conditions. I'll try to draw it with a diagram. Okasari clarity vachestundi. Like say, if this is your one shell, and here there is your energy right now. This is one shell, and here there is your another shell, and here there is your another shell. మరి దగ్గరలో ఉండాలి కదా, ఎనర్జీ కొంచెం తగ్గుతుంది. So this one is nearer, and this one is your final condition, somewhere more nearer. Okay, this one is your K shell beta, this one is your L, this one is your M, this one is your N. This is your energy up to infinity అనుకుందాం. This is your energy of your infinity. So when there is a transition from your higher energy level, like say for example, this is your energy of your L, this is your energy of your M, this is your energy of your N, this is your energy of your infinity. If there is a drop of electron from your L to your K, that is known as of what? K alpha. If there is a transfer of an electron from your M shell to your K shell, this is known as of your K beta. Then if there is a transition of electron from your N to your K, this is known as of your K gamma. Okay. In the same way, if there is a transition from your M to L like this, this one is known as of your L alpha X-rays. Then from your N to your this one, this is known as of your L beta. Okay. The same way, from higher orbit, if I am taking right now here, this one, now from your N to your M form, it is been coming from your N, it is being incident onto your M. This will be equal to your M alpha X-rays. Okay, so like that we can go on take the relations for this one. So ultimately what I can write, energy of your K is greater than energy of your L, energy of your L is greater than of energy of your M shell is greater than, so on up to the given condition. Energy of K, L, M and all of them are what beta? Positive hai kada? Energy of K shell, energy of L shell, energy of your M shell, so on are what? Positive. So on of what right now for me? Positive. That means if I'm writing for wavelength of your K alpha, wavelength of your K alpha, that will be equal to your H into C divided by energy will be K alpha ante inte ekkadi nunchi vastunam manam right now. We are coming from your energy of K is more compared to your L. So we'll be writing this one as of your energy of your K minus energy of your L. Antena? In the same way, if I'm writing lambda K beta, wavelength of your K beta radiation, so that will be equal to your HC divided by energy of your K minus energy of your M, K beta K. In the same way, if I am writing lambda of your K gamma, that is equals to your HC by energy of your K minus energy of your N. So like that I can write the given condition. Alpha, lambda of K alpha, K beta and wavelength of your K gamma part of relation. So the characteristics wavelength will depend upon the target material beta. This will depend upon what? Target material. I can write that point here right now. The characteristic wavelength, the characteristic wavelength depends on target, depends on your target material. So 1 by lambda is equals to Z minus of your B whole square into 1 by N1 square minus 1 by your N2 square. So this is the relation we'll be using to calculate the wavelength of your characteristics of your X-rays. What is the Z beta here? Z is your atomic number. Z is your atomic number of target atom, of your target atom. B is your constant. B is your constant due to screening effect. Due to your screening effect. That value will be given, don't bother. And B value is equals to 1 for your K alpha X-ray. K alpha X-ray. Clear? Keep a note beta here. X-rays of high frequency, of your high frequency or low wavelength are called hard X-rays, or called as what? Hard X-rays. So what are hard X-rays beta? Whose frequency is more or wavelength is very, very large part of relation. Wavelength is very low. In the same way, X-rays of low frequency or high wavelength are called soft X-rays. Okay. So we got two formulas to be remembered. Continuous X-rays దేనిపైన డిపెండ్ అవుతుంది? And what is the minimum wavelength of an X-rays? Minimum wavelength of your X-rays is hc by E into your V, where V is nothing but of your accelerating potential. Characteristics of your X-rays part affiliations are emitted by the vacancy. They are being transitioned from the given condition. So if vacancy has been created from particular, they are called as of your characteristics type of your X-rays part affiliations. So we have got lambda of K alpha, wavelength of your K beta, wavelength of your K gamma, go on like that. Then what do you mean by hard X-rays and soft X-rays? So this is your hard X-rays and this one is your soft X-rays. The X-rays whose frequencies vary high frequency and low wavelength, or low frequency and high wavelength, are called as of your soft X-rays. Okay. The next one is last part of this one, Moseley's law. Moseley's law. మీరు already atomic structure లో చదివింటారు. What do you mean by the Moseley's law? Moseley measured the frequency of characteristics X-rays beta from a very large number of elements, and he plotted a graph between the frequency and the position of your number, and he got some graph. That graph only we are calling it as of your Moseley's law part of relations. So according to Moseley's law, the element in the periodic table should be arranged in the ascending order of atomic number, but not of your atomic weight part of relation, isn't it? So the elements in periodic table, the elements in your periodic table should be arranged in ascending order, of your atomic number and not atomic weight. And not atomic weight. Okay, so it is the graph actually between the frequency, that is root of your frequency, versus your position number, So we got a graph something like this from here for different elements. Okay, so mathematically the formula is given by root of your mu is equals to your a into your z minus of your b, where mu is your characteristic frequency of a particular atom, z is your atomic number, a and b are constants, depends on nothing better. They are right now just a constant part of relation. Okay, and even in this one there is one more formula to be remembered. We don't have a proof of this one better, just remember for the given condition, absorption of X-ray, your X-ray. Okay, that means when a ray of light is being incident on any of this.
Sir.
Beta.
So previous diagram position
versus graph mala mostly actually measured the frequencies of characteristics beta. Mostly actually what he did is, I can write here right now, mostly he actually measured frequencies of characteristics X-rays. Ante okka orbit lo he started producing the energy from that X-rays from a large number of elements, your elements. Okay, so when he started doing this one, he found that the X-rays which have been coming out is depending upon the position of the number. That means every element will not produce the X-rays. But మనం hydrogen తీసుకున్నాం, neon తీసుకున్నాం, potassium తీసుకున్నాము, has never got an X-rays. he told that this X-rays can be gotten by only with this particular atomic numbers, with your higher atomic number like of your iron, molybdenum, zinc, isn't it? So such type of your metals can only will produce you the X-rays particulation. He started doing the experiment with the first atomic number. He has found nothing. X-rays have been targeted. Target element he take it hydrogen, neon, then sodium, potassium. Alanti iskunta poyadu. He couldn't able to get any X-rays. At a particular atomic number, he started getting the radiations. Then he started doing it with lot number of elements, and he says that at a certain particular frequencies, the square of your frequency is directly proportional to your position of your atomic number. So he had given that root of this frequency is directly proportional to your atomic number, and some experimental values we got the relation as root of your mu is equals to your A into your Z minus B. Like characteristics X-rays we got for your certain minimum ante immediate ga raledu. So when you are doing an experiment, as the intensity was being slow on increases at a particular wavelength, it started producing the X-rays partitions. That wavelength at which there was intensity was been increasing is called as what? Minimum wavelength. In the same way, for the protection of your characteristics X-rays partition, we should be having a particular atomic number. That particular atomic number will only give an X-rays. That atomic numbers are starting from your higher numbers of your atomic number, like say molybdenum, zinc, isn't it? Like the type of your molybdenum, zinc, platinum. This all have been target elements by which we have been producing the X-rays partitions. And with lot number of an experiment, he got a proof that root of your mu is equals to your A into your Z minus B, where A and B are constant and Z is your atomic number partition. Okay, now this is like a straight line equation. Y is equals to M into your X partition. Constant will be negative downward direction, but the graph will not pass from the origin part. Okay, now. Absorption of an X-rays beta. So when the X-rays were being incident on any surface, then intensity I naught unnankon. This part of the region, that is nothing but X, will observe certain radiations, and coming out radiation will not be the same, but it will be something of your I. So this intensity is given by the formula I is equals to your I naught exponential to the power of minus of mu into your X, where I naught is your intensity of incident X-rays. I naught is your intensity of your incident X-ray. Incident X-ray. And I is your intensity of emergent ray. It is your intensity of your emergent X-ray. Emergent X-ray. And mu is your absorption coefficient. And mu is your absorption coefficient. Okay. The last formula of this one, which you already studied in your chemistry, I'm not doing the derivation of this one. That is about your Bragg's law. Bragg's law. Gurtunda chemistry chadivaru Bragg's law. X-ray might be diffracted by suitable diffracting centers. Gurtunda. So if this is your certain layer, and there are certain electrons which have been present in this one like this, isn't it? So distance between any two this layers is nothing but how much for me? D. When the ray of light was being incident on this one at a certain angle, it was getting refracted. So this one is theta, and this one is also your theta partition, isn't it? So X-rays may be diffracted, by your suitable diffracting centers. The formula for this one is 2d into sin theta is equals to your n into lambda, where n is equals to how much beta? 1, 2, 3, go on. And d is your what? Interatomic distance. D is your interatomic distance. Theta is your angle of incidence. Theta is your angle of your incidence. And lambda is nothing but wavelength of X-rays. Wavelength of your X-rays. So మొత్తం X-rays లో మనకు ఉన్నవి రెండు ఫార్ములాస్ మూడు ఫార్ములాస్. ఒకటేమో వేవ్ లెంత్ ఫార్ములా, ఇంకోటేమో ఇంటెన్సిటీ ఫార్ములా. I is equals to your I naught into mu into x, and last one is nothing but of a Bragg's equation formula, that is 2d into sin theta is equals to n into lambda, where d is your interdynamic distance, n is nothing but of your integers, and lambda is nothing but wavelength of your X-rays part of a relation part. Now for the properties of an X-rays, you please try to refer your NCERT beta. That X-rays travels in a straight line in a vacuum with the speed of your light. X-rays are not deflected by electric and magnetic field. X-rays are diffracted in the crystals, and according to the Bragg's law, X-rays affect the photoelectric plate, which was strongly visible region. They can ionize the molecules of the gas. They can cause the fluorescence. They can penetrate into several metals. These are all the some of the properties of an X-rays, which you can try to do it out from your material part of relation. Let us try to do some problems on this one, beta. First problem. The wavelength of the characteristic X-ray K alpha line emitted by an hydrogen-like atom, emitted by a hydrogen-like element. Hydrogen-like element is 0.32 angstroms. Calculate the wavelength of K beta line emitted by the same element. Student sir, the wavelength of your characteristics X-rays like K alpha. So characteristics X-rays ki formula you use chestamnanu 1 by your lambda is equals to Z minus of your B whole square into your capital R into 1 by your N1 square minus of your 1 by your N2 square. K alpha line of an hydrogen like atom. Now see, for K alpha line, K alpha is equals to 1 by wavelength of your alpha is equals to Z minus B whole square into R is into 1 by, this one is your 1 square minus 1 by your 2 square. K alpha ante this will become for me how much? Z minus of your B into your whole square into your R into 1 minus 1 by 4. So this will become for me 3 by 4. Isn't it? The same way for K beta, if I am talking about, for your K beta ఎక్కడి నుంచి వస్తుందన్న? It is coming from your M to your K. So this will become for me 1 by lambda of your beta will be equal to your Z minus of your B whole square into your R into, this one is 1 by 1 square minus 1 by third orbit నుంచి వస్తుంది కాబట్టి 3 square. So it is 1 by 3 square is nothing but 9. So this will become for me z minus of your b whole square into your capital R 1 minus 1 by 9. So this will be equal to your how much? 8 by 9. So this is 1 by lambda of your beta. Okay now? What is the wavelength of the characteristic X-ray K alpha line emitted by the hydrogen like element is 0.32 angstroms. Wavelength of K alpha is manaku. Calculate the wavelength of your K beta part of relation. That's it. So if I am taking the ratio of this one right now, see what I am writing for this one. This one is lambda of your beta divided by lambda of your alpha is equals to, this one will become for me 3 by 4 divided by this one is nothing but of your 8 by 9 ante kada 1 by alpha kabatti. So that will be equal to your 27 divided by your 32. 3 9s are 8 4s are. So we need to calculate the wavelength of beta divided by wavelength of alpha is 0.32. So that is equals to 27 divided by 32. So wavelength of your beta will be equal to 0.32 into your 27 divided by 32. So this will become for me 0.27 angstroms. Ante kada 32 0.01. So it is 0.27 angstroms will be the answer for that. Okay now? Clear? Let us try to do one more question better. The K alpha X-ray, the K alpha X-ray molybdenum metal, molybdenum has wavelength 71 picometer. If the energy of a molybdenum atom with a K electron, with your K electron is knocked out, is knocked out is 23.32 kilo electron volt. What will be the energy? What will be the energy of this atom? When an L electron is knocked out? Very good question. Try to read it twice before you go for the working of this one. The K alpha X-ray of your molybdenum has a wavelength of how much beta? 71 picometer. 71 picometer. If the energy of the molybdenum atom with a K electron knocked out is 23.32 K electron volt, kilo electron volt. What will be the energy of this atom when an L electron is being knocked out from the given condition? You already know how to write the energy relations beta, isn't it? So energy when it is coming from one orbit to another orbit right now, energy of the K orbit will be greater every time. Energy of your K minus energy of your L will be equal to your h into c divided by your, this one is lambda into your k into alpha. అంతే కదా. Wavelength of your k alpha ఎంత ఇచ్చాడు? Wavelength of your k alpha is given as 71 picometer. So that will be equal to 0.071 meters, nanometers. అవునా కదా. So now if I'm writing the energy in the electron volts beta, so energy in your electron volts గనక రాసుకుంటే this will be 1242 divided by wavelength in your nanometers. Wavelength in your nanometers అంటే that will be 1242 divided by, this one is 0.071. So simplify this one, we'll be getting the energy in electron volt. This one is approximately 17.5 into 10 to the power of 3 electron volt, or else I can write this one as 17.5 kilo electron volt particulation. That means energy of the K shell minus energy of your L shell is equals to capital E. So energy of the K shell in the 23.32. We need to calculate the energy of L shell. Energy of this orbit enta manaku 17.5 kilo electron volt. That means energy of your L orbit will be equal to how much for me? 23.32 minus 17.5. So 23 minus 17 enta 5. And this one is 32.5. ఎంత వస్తుంది? 5.82 kilo electron volt. So this will be the energy of your nth orbit.